In this video, we're going to cover section 3.8 on implicit differentiation and logarithmic differentiation. So the two objectives of this section are to learn how to differentiate implicitly and to use logarithmic differentiation to find the derivatives of certain functions. So before we move on to the first example, implicit differentiation is a method of finding a derivative when your equation or your function cannot be solved for y. If you remember, when we're finding a derivative, we're finding the derivative of y with respect to some variable. So when you can't solve your equation for y, you're assuming it's a function of x, and you still need to find the derivative with respect to x, but you can't isolate y. So we can still use our regular rules, but we have to do a little bit more algebra. Logarithmic differentiation is useful when you're differentiating something that involves products, quotients, and powers. All right, because utilizing logarithms on those things allows you to simplify them. So when we get to that part of this section, we'll review what those rules are. All right, so our steps for finding the derivative using what we call implicit differentiation. All right, to differentiate implicitly, meaning you're going to start by taking the derivative of both sides of the equation with respect to x, or whatever variable you're supposed to be finding the derivative with respect to. Usually it's x. Occasionally it's something else like t or whatever. So we take the derivative of both sides of the equation with respect to x. Okay, and as you do that, you have to keep in mind that when you see the variable y, it is a function of x. It's just you don't have the y all by itself on one side. All right, so when we think about it that way, we apply the rules of differentiation as necessary. So you'll have to recognize when you're needing a chain rule or a product rule or a quotient rule. Anytime the expression involves y is being differentiated, you always follow it with dy dx. The reason for that is it's an application of the chain rule. Remember, the variable y is a function of x, so finding the derivative of y is like the dy dx part is the derivative of the inside. Okay, so we'll see that here in the next few examples. Isolate, once you've done your derivative implicitly, step C, or third step, isolate the terms that contain the dy dx factor. So anything that has a dy dx attached to it, you want to move all those terms to one side of your equation. Put any term that does not involve the dy dx piece to the other side. Next, once all those terms containing the dy dx are isolated, you can factor out the dy dx part. And then you'll be able to divide both sides of the equation by whatever's left to isolate your derivative. So you're still finding the value of dy dx when you're finished. Typically, your answers for these problems contain both x and y, not just x like they did before. I know this is confusing to read these steps in words, so we'll go through several examples here to show how they work. All right, so our first problem here, we have y cubed plus x squared y to the fifth minus x to the fourth equals 27th. This is a perfect example of an equation that we would have to differentiate using implicit, because we can't get y by itself on one side. All right, so we're going to find dy dx using the implicit process. Then they want you to find the slope of the tangent line, which just means evaluate the dy dx result at a given value of x and y, at a point. So in other words, when x is 0 and y is 3. All right, so before we can do that, we have to find our dy dx. All right, so we're going to take the derivative with respect to x of the left, so the derivative with respect to x of this y cubed plus x squared y to the fifth minus x to the fourth equals, then also take the derivative with respect to x of the other side. So differentiate both sides with respect to x. All right, so notice here, we're going to go term by term. So this contains y. So when we take its derivative, we would get 3y squared, but because it involved y, we follow it with dy dx. Plus, the middle term is a product, so we have to utilize our product rule. And when we differentiate the term involving y, we can't forget our dy dx. So let's think about the product rule first. So the first function is just x squared. that gets multiplied by the derivative of the second. So this derivative would be 5x to the fourth, 5y to the fourth, and then because it's y, we follow it with dy dx. So in the product rule, that's the first part. Then we plus, this time we leave the second function alone, y to the fifth, and multiply it by the derivative of the first. So the derivative of x squared is just 2x. Notice there's no dy dx attached because I did not differentiate anything that involved y. This was just the original function, and then the derivative of this thing, the thing I was differentiating, did not have a y in it. So all of this, starting right here with this x squared, all the way through this 2x part, that's the product rule for differentiating the middle term. Minus, then this derivative is just 4x cubed. So because it doesn't involve a y, it's just the normal derivative, and that's it. Equals, the derivative of a constant is 0. Okay, so this is that first step of noticing how to apply implicit. Notice this factor has a dy dx, this term right here has a dy dx, but these do not. So our next step is to isolate all the terms containing dy dx. So what we're going to do is we're going to move this term and we're going to move this term to the other side of the equation. All right, so what they've done here is think of it as they're leaving these two terms on the same side, and because they are the only terms that contain dy dx, they factored that out. So that would leave a 3y squared plus a 5x squared y to the fourth, okay, equals this 2 x y to the fifth has been moved over, and so has the 4x cubed. So the 4x cubed has been added, and then this 2x y to the fifth has been subtracted over here. So just some algebra rearrangement. And now we can just divide both sides by this set of parentheses to get the dy dx by itself. So we're going to end up with the 4x cubed minus 2xy to the fifth divided by this other thing. And that's our result. All right, so then part B, find the slope of the tangent line at 0, 3, basically means the slope of the tangent line still means the value of the derivative. So if I'm evaluating at this ordered pair, I'm letting x be 0 and y be 3. So if I plug in 0 for x and 3 for y into my derivative, x's get replaced with 0s, y's get replaced with a 3. Looks like that. And then when you clean that up, notice this is a 0 on top, so is this. This top is a 0. This term is going to be a 0, and this term is going to be 27. So you're going to get 0 over 27, which is just 0. Okay, so let's try another one. For y squared x plus 2x cubed y cubed equals y plus 1, find dy dx using implicit differentiation. All right, so again, step 1, derivative of both sides with respect to x. All right, so this left side we're going to have two product rules. This first term is a product of y squared times x. We have to use the product rule there. The second term is also a product of this 2x cubed y cubed. All right, so our product rule here. So they started here with the derivative of the y squared, so that's the 2y dy dx times the other piece of it times the x, plus then just the y squared left alone times the derivative of x, which is 1, so they didn't write it. All right, plus then they're going to use the product rule here. So here we're going to leave the x cubed as it is. When I differentiate, and then remember that 2 just stays in front as a constant. So x cubed stays, let's differentiate y cubed. That would bring down the 3, giving me the 6 y squared. So the 6 y squared dy dx, because there's a y there, times your x cubed part, plus this time we're going to leave y cubed, and we're going to differentiate the first term here. So it's going to be 6x squared. That's the derivative of that first part times the second. Because I differentiated an x and not a y, I don't need a dy dx. Equals, this derivative is 1, but it's y, so it's 1 times dy dx, and then that derivative is 0. All right, so this time I've got a dy dx over here. I've got a dy dx in this term and in this term. So this time we're going to move these two terms to the right side. We're going to subtract them over. So we're going to leave the y squared where it's at because there's no dy dx attached to it. And we're going to leave this 6x squared y cubed where it's at. All right, so they stay on the left, equals. This was already here. We subtract this over, so it's minus the 2xy dy dx. And we subtract this over, minus 6. This should say x squared y cubed. Sorry, I didn't catch that. They have that meant. Oh, no, I'm sorry. This is the one we're moving. So it's correct. Minus 6x cubed y squared dy dx. So we're moving this term. So there's no mistake there. All right, then we can factor the dy dx out of the things on the right, leaving the 1 minus 2xy minus 6x cubed y squared. This factored out. Nothing changed over here. And then we just divide by this stuff in front. So we end up with y squared plus 6x squared y cubed divided by all of this. And that's our answer. All right, so in this next example, they want us to use logarithmic differentiation. All right, so given this function y equals, notice this one is not set up for implicit, right, necessarily, because it's a y equals some function of x. That's the difference. So we could do this the way we have learned previously. It would be messy and complicated because it would involve a product rule, because there's a product. Differentiating this would involve the chain rule, and differentiating this would involve the chain rule and fractions, etc. So it would be kind of a mess. All right, so the reason logarithmic differentiation to find our derivative is helpful is because this is a product, and within the product we have things that are raised to powers. Okay, so let me show you how logarithmic differentiation makes this a simpler derivative. So we're going to start, when it's called logarithmic, we start by taking the natural log of both sides. So we're not going to start by taking a derivative. We're going to start by just taking the natural log of both sides of that equation. So the natural log of the left is just the natural log of y equals the natural log of this right side. Okay. All right, now the reason we did that is because we said we have a product, and within the product we have things raised to power. So now we can simplify this right side using properties of logs. So the first thing here, that the log of the product we know splits up into the log of the first plus the log of the second, right? It splits up into a sum. Next we have the log of this thing that has a power. So our power property of logs brings the 3 down to the front. So this becomes 3 natural log of this inside part. The square root, remember, is the power 1/2. So you're bringing down the 1/2 exponent, and then you're left with natural log of what was on the inside. So we haven't done any derivatives yet. We've just taken the log and we've used our properties to expand as far as we can the other side. The benefit of that is, now, if I tried to differentiate, I no longer have to worry about using product rule. Because this is no longer a product, it's just a chain rule with a log in it, and so is this. Okay, but the issue here is now we have to, when we take the derivative, we have to imply implicit, because this left side is no longer just y, it's natural log of y. But the good thing here is that the only place y is located is on the left. You're not going to have any y's over here, so it's not going to be as messy of an implicit process. So implicitly take the derivative of both sides with respect to x. So this derivative would be 1 over y. Right, that's the derivative that involves a log, but it's because there's a y there, we have this dy dx attached, equals. So this first term's derivative, the 3 would just stay in the front. Remember, a log's derivative is, it's 1 over what's on the inside, so this goes on the bottom, and then it's times its derivative, right? So the derivative of that inside goes on the top, so that's 4x cubed plus 3. So it's just the derivative on the top divided by what was inside your log. Plus, same thing here, the 1/2 constant can stay. This is just, again, the log of some function, so it's 1 over what's on the inside, that goes on the bottom, and then the derivative of that inside goes on the top. So the derivative of 1 is 0, and then you got minus, this would be 15x to the fourth. All right, so now the only thing left to do is to solve for your derivative. They're going to clean this up here first, though. So they've distributed your 3 into the numerator. So that's 3 times 4 is 12, and then 3 times 3 is 9, leaving the bottom. And then cleaning this up over here, the negative they just pulled out to the front, multiplied the 1 times that other numerator, just giving me this with the negative in the front, and then the bottom just made a complete denominator out of. You don't have to go any further than that. You don't have to get a common denominator and do the actual subtraction, but you should clean up each piece. The left side did not change. So our next step is we're going to solve for dy dx. We're going to multiply both sides by y to get rid of that here. So remember, this was 1 over y dy dx, so times y cancels it, and it shows up over here as this whole side times y. But remember, we knew what y was from the very beginning. It was this was what we were given as y, right? Y was equal to this function. So you could just replace this y with what the original function was. So the original function, which is the y part, and then times what we got within that logarithmic differentiation. And then that's the answer. All right, so this is another one that would work the same. So if you want to pause the video and try to do this on your own using the previous example as a guide, that would be a good idea. So you can pause it and try it, and then you can press play to follow along to see if your end result was correct. All right, so if we're given this function, this is a quotient that has an exponent applied to the top and the bottom, so that's why logarithmic would be helpful here. Without it, we'd have to use the quotient rule, and within it, we'd have a messy chain rule, and it would be a little bit more complicated. So use logarithmic differentiation. We're going to start again by taking the natural log of both sides. So the natural log of the left equals then the natural log of the right. Now we simplify using properties of logs, mainly simplifying your right side. So the first thing here is we have a quotient. So we're going to start by splitting it to subtraction. So the log of the top minus the log of the bottom. Next, again, our power property allows the powers to come down. So 4 comes down the front of this one, and then this cubed root, remember, is 1/3. So that 1/3 power comes down in front of the second one. The left side does not change. Now we're going to differentiate implicitly. So we're going to take the derivative with respect to x of both sides. So this left side, again, is going to be 1 over y, but because it's y, it's dy dx. It's the implicit process, equals. The 4 stays. Again, the log derivative is 1 over the inside function, and then the numerator is the derivative of what's on the inside, 2x plus 5. Same thing here, minus the 1/3 stays, 1 over 5x minus 7 times the derivative of the 5x minus 7, which is just 5. So next we're cleaning up the right, so 4 distributed through here is 8x plus 20, keeping that on the bottom. Over here, that's 5 on top, and then 3 times 5x minus 7 on the bottom. And you can keep that in parentheses with the 3 outside, or if you distributed the 3 through there, it probably would be fine. All right, so lastly, then we got to multiply both sides by y. Actually, they did go ahead and distribute the 3 here. So multiplying both sides by y puts that y on the other side, and then replacing y with what we were given for y ends up giving me this. So this y gets replaced with what we were given as y, and then times the result of my differentiation. All right, so our summary for this section. Okay, if variables x and y are related to one another by an equation, but neither variable is isolated on one side, that's when we have an implicit situation. So to find dy dx without solving the equation for y, right, we follow the implicit process. Whenever we implicitly differentiate y with respect to x, don't forget that the dy dx factor will appear anytime you differentiate a term involving y. That's a result of the chain rule. And then logarithmic differentiation can be used to differentiate certain functions, particularly ones that have products, quotients, and powers. To do this with a function, we take the natural log of both sides first, and then we differentiate implicitly after we have simplified the right. All right, so that is the end of section 3.8.